Who knows this tune?
I do. Orion.
Very astronomical too. Okay, thank you all for coming. This is my first performance at Astronomy on Tap. I hope to do well so they can invite me back. I'm here to tell you the basics about black holes, and hopefully I will introduce the subject for the next speaker, who's going to tell you a lot more about what we're doing today in the astronomical community about black holes. So, to introduce you to the concept of a black hole, I have to start with something extremely basic. Okay. I'm sure you all know that if I throw an object up in the air, if I throw a baseball up in the air, it goes up to some height, and then it turns around and it comes back and falls down. If I throw it harder, it goes even higher, and then it comes down again. And the harder I throw it, the higher it goes. And most of the time, it will come down. Okay. The reason it comes down is because it uses up all the energy I gave it on launch. It uses it up to climb to a certain height. All of its kinetic energy is converted to potential energy. And then at some maximum height, gravity essentially stops it, turns it around, and brings it back. Okay. However, there is a magic speed. And in the case of the Earth, that magic speed is 11.2 kilometers per second. If I throw my projectile, my baseball, at that magic speed, it will actually be able to break free from the Earth's gravity. I've given it enough kinetic energy to overcome the potential energy from the Earth's gravitational attraction, and it will keep going. It will never come back. That's called the escape speed. The escape speed for the Earth, 11.2 kilometers per second. That's a huge speed, right? It's kilometers per second. Multiply that by 3,600 to get it into kilometers per hour. So it's huge. Now, the escape speed depends on the properties of the planet. If you make the planet more massive without changing its size, the escape speed goes up because the force of gravity increases. If you make the planet more compact, if you squeeze the Earth and make it smaller without changing its mass, the escape speed will also increase because now you're closer to the center. For the same amount of mass, the gravitational pull is the same. So essentially the escape speed is in a sense a measure of the density of the planet. You start making the planet denser and denser, either by adding mass or by squeezing it, then the escape speed from the surface gets bigger and bigger. So what would happen, you think, if the escape speed got to be equal to the speed of light? Ben, what would happen in that case? Can anything go faster than the speed of light, Ben? No. Very good. The speed of light is the universal speed limit, and it's a huge limit. It's an enormous speed. It's 300,000 kilometers per second, which amounts to, I think, 675,000 miles per hour, or something like that, some enormous number. And if I wanted to go to Pittsburgh, to the airport at the speed of light, it would take me 1,000th of a second to get there, which is always what I strive to do, but I've never succeeded. So that is the speed of light. Okay? So with this in mind, I can now tell you about the concept of a black hole. A black hole is an object, and it doesn't matter what it is, what it's made of, for which the escape speed from the surface is higher than the speed of light. So anything that's sitting on the surface, if such a thing exists, if such a surface exists, would never be able to escape from the black hole because it could never launch itself faster than the speed of light. So it's stuck there. Not even light can escape. So that's the basic idea. And this concept historically can be traced back to the mid-1700s when John Mitchell and Pierre-Simon de Laplace, the Marquis de Laplace, came up with this idea. I think they were motivated by Newton's corpuscular theory of light. Newton supposed that light is made up of little particles, and they went one step further from there, and they said, well, if light is made up of particles, then they should be subject to gravity, and if we had a planet that's extremely dense so that the escape speed is higher than the speed of light, those particles would never escape the planet. And the planet would not radiate any light, so it would appear dark. And that's where the name black hole comes from, essentially. The theory was made more formal by Einstein in 1915. A year later, Carl Schwarzschild came up with the first formal concept of a black hole. Okay. So here's an example of a black hole right there, as imagined by Einstein, by Laplace. Okay. So let me help you a little bit. There it is. It glows a little bit, and that's the center of the sphere. So that circle represents the event horizon. And what's the event horizon? You can write down an equation for it. And the event horizon is a mental boundary. Within the event horizon, the escape speed is larger than the speed of light. And outside of the event horizon, the escape speed is a little lower than the speed of light. All of the mass of this object is concentrated at the center, in that red dot. So you could pack more mass in the red dot, and the event horizon gets bigger. And so the region within which you are stuck gets bigger. As stuff falls in, it gets incorporated into the mass of the black hole, and the black hole grows, so to speak. When we speak of the size of a black hole, what we really mean is the size of the event horizon. So that's the basic idea, and they're very intriguing mathematical objects. Physicists love them. As astronomers, we have a more practical point of view of them. We wonder whether they can exist in practice. If they can, how do we find them? How do we measure their properties? And what can they do for us? And that's the topic of the talk that I'm going to give you. Okay? So we know of two types of black holes. The ones we call stellar mass black holes. They have masses that are of the same order as the mass of the sun, maybe up to 30 times the mass of the sun. And then the other flavor, they're called supermassive black holes. They start at 1 million times the mass of the sun. Okay. So how do stellar mass black holes form? We have a pretty good idea of how they form. What you see in this picture is cartoons that show you the life sequence of a massive star. Actually, the events at the end of the life of a massive star. The star has spent most of its life supporting itself against gravity by generating energy in its core. And its core is a fusion reactor, where hydrogen fuses into helium. It produces a lot of energy. That energy keeps the interior of the star hot, and the outward pressure resists the weight of the outer layers of the star and keeps the star stable. As it runs out of hydrogen, it starts to fuse heavier elements. Helium into carbon, then it adds helium nuclei to carbon, gets nitrogen, oxygen, and keeps producing heavier and heavier elements by fusion in the nucleus. And as the star gets older and older, it builds up the ash of all these fusion reactions. You see here, the core is made up of iron, so the fusion process went all the way up to forming iron, and then there's shells, successive shells around that, where fusion of other elements continues, right? Helium fusion, hydrogen and helium fusion in the outer layers, carbon, oxygen, neon, magnesium, silicon, all the way in, and then all the accumulated ash is iron, and it builds up in the core. And iron is the end of the line, basically, because iron cannot fuse into anything heavier and give you energy. In the language of chemistry, the fusion of iron is an endothermic reaction. So you need to put in energy to make that happen. So it doesn't happen naturally. So once the star builds up a core of iron, that's basically it. It runs out of fuel. There's no more fuel to burn, and it very quickly, through a sequence of events that happen over the course of a few minutes, the star loses all of its pressure support. So it has no way of resisting the pressure of the outer layers that are weighing down. So the outer layers essentially crush the core. The iron core is an object that's about the size of State College, and it has a mass that's about a few times the mass of the sun. It's an extremely dense object, and it comes crashing down when pressure support is lost. It crashes into a much smaller object in a time of a second. So That's what you see in this cartoon here. The massive star implodes, the iron core comes crashing down, and then it rebounds. Comes down, then rebounds, and the rebound sends a shock through the envelope of the star and blows away the envelope.
Mike, can you maybe speak a little closer into the mic and a little louder?
Okay, like this.
Yes.
So the core rebounds, sends a shock wave into the envelope of the star and blows it up. That's what we call a supernova explosion. The whole star blows up. What used to be the core remains as a ball of neutrons in the end, or it might come crashing down and become a black hole. A star that is up to 8 times the mass of the sun, between 8 and 20 times the mass of the sun, when it dies in this manner, the core won't be massive enough to crush itself. It will become a ball of neutrons and remain stable. If the star is from about 20 to 60 times the mass of the sun, then even the core itself will be crushed by its own gravity and turn into a black hole. And we know that these things happen. We know that supernova explosions happen. We observe them all the time. This is one of the more famous supernova explosions, supernova 1987A. For a few weeks, this star right here that exploded in the Large Magellanic Cloud was a lot brighter than the entire galaxy that it lives in. So you see in this before and after picture a little dot that represents the initial star, and now you see how much brighter it is. So the star can get up to 1 million times brighter for a few minutes. We also know the sites of old explosions. These are supernova remnants. They're the debris that was thrown out by the star during the explosion. Okay, this is the Crab supernova remnant. The explosion was actually observed in 1054 AD. That's the Cassiopeia remnant. It's about 300 years old, but we don't have any record of anyone actually witnessing the explosion. So at the centers of both of these remnants, we know there are neutron stars. We've observed them. So we know also that black holes can form in the same way. And it's not a stretch then to figure out how black holes are formed. We also know how to measure their masses. And we find, with the methods that are available to astronomers, that their masses can be anywhere from a few times the mass of the sun all the way up to 10, 15 times the mass of the sun. And as you will hear in the next talk, they can get even a little more massive than that. The other flavor are supermassive black holes. And those live at the centers of nearby galaxies, at the centers of all massive galaxies, and we can observe them very well in nearby galaxies. So this fuzzball you see in this picture is the giant elliptical galaxy M87. It lives in the center of one of our nearby clusters of galaxies, the Virgo cluster. And if you look at it with a telescope and take a picture of it, it looks like nothing special. It's just a fuzzball. But if you look at it with a radio telescope, the view that you get is completely different. This is the very large array. It's an array of 27 dishes, radio telescopes, in the desert in New Mexico near Socorro. It's a little south of Albuquerque. You see the railroad tracks, and the antennae can ride on railroad tracks, and you can make the array expand up to 20 miles. You can get all the antennae to work together as a single telescope. And the bigger the telescope is, the more exquisite detail it can reveal. So when you observe with this telescope, this is what you see. This looks nothing like the optical picture of M87. The galaxy that you saw in the earlier picture would look that big on this scale. And if you zoom in further, you see this jet of gas that's being spewed out from the center of the galaxy. So this is ionized gas that's being kicked out from the center at a speed that's very close to the speed of light, more than 99% the speed of light. And what happens in this case is that gas that's been captured by the black hole and it's brought in, as it spirals around the black hole before it falls in, it's redirected by a magnetic field and it's turned into this collimated jet that's shot out from the center of the galaxy. And it can expand out to distances bigger than the size of the galaxy itself. These lobes that you see here, they're filled with this plasma, and their extent is bigger than the size of the galaxy. Okay? So this is one of the ways that we find black holes when we couldn't have seen their signature in any other way. If we now go and use our best optical telescope, this is the Hubble Space Telescope, yeah. Our best optical telescope, it gives us the best resolution. And we take a picture of M87. With 20/20 hindsight, we know what to look for. We actually can find the jet. And we can trace down to the base of the jet. And we can look at the details of what's going on. This picture is taken in the H-alpha line of hydrogen. This red glow is a telltale sign of emission by hydrogen atoms. Okay? In this particular case, the hydrogen gas is swirling around the black hole. Think of what happens when you pull the plug in your bathtub and the water swirls around the drain and then eventually goes down. In this case, there's no down, there's in. The water comes in, or the gas comes in, and it falls into the black hole. We can actually measure the speed of the gas. We can take observations all around, measure the speed of the gas as it goes around the black hole, and from those measurements we can figure out its mass. And the mass that is measured is about 4 billion times the mass of the sun, 4 times 10 to the 9 solar masses. And this is not the record holder. The record holder is even more massive, 2 times 10 to the 10, 20 billion times the mass of the sun is the record holder. We have one supermassive black hole in the center of our galaxy. The way we measure the mass of that black hole is by following the motions of stars that are going around it. It's easier to follow the stars in that case. And, there's 2 groups that do these observations. There's a group at the Max Planck Institute in Germany and another group at UCLA, California. So I'll show you 2 movies. The first movie on the left shows you the motion of the stars around the black hole. The black hole is marked by a cross in both cases. And the way they make the movies, they take an image every year, they go back, they take an image, and then they assemble the images into a movie. So this movie runs from 1992 to 2003. Watch how the stars move. Okay? The stars closer to the center move faster than the ones further away. And that's because the gravity of the black hole that controls their motion is a lot stronger. Let's do this again. Okay. Now, let's go to the movie on the right. The time span is a little longer. Okay, zoom in on that box and watch the trajectories of the stars. Okay, for illustration, you see all the measurements that were made before the movie was put together. Okay, so all the measurements show you the position of the black hole at different times. You can plot the trajectories, and by combining the trajectories of all the stars with their speeds, you can actually get the mass of the black hole to great precision. And in this case, you can also prove beyond doubt that this object must be a black hole. There's no other object that is massive enough and small enough to fit in that space. And the mass that we get here is 4 million times the mass of the sun, 4 times 10 to the 6. So, black holes are not only interesting to physicists and mathematicians, astronomers love them because they play an important role in a lot of things. Today we appreciate that they play an important role in the evolution of galaxies. That some of the gas they capture, they spew out, they don't swallow it all. And that outflow from the vicinity of the black hole is an important process that cleans out gas from the host galaxy, and it plays an important role in shaping the properties of present-day galaxies. It influences the evolution of the host galaxy profoundly. That's only one of the things they can do. They also do things that that happen on much shorter timescales. They can destroy stars that get very close to them. So I'll tell you 2 examples of how a bright star can find happiness in the deadly embrace of a black hole. Let's start with supermassive black holes. And the concept I have to explain first is the concept of tides. We know about tides from the Earth. This is how tides work. There's the moon, and the gravity of the moon is acting on the Earth. Every arrow here represents the force of gravity from the moon onto that spot on the Earth. And it shows you the direction as well as the magnitude. The near side of the Earth is a little closer to the moon, so it's pulled a little more strongly than the far side. And at the top and the bottom, the arrows converge towards the center of the moon, so not all the arrows are parallel. So if you look at the differences between all of these forces, you find that the forces are equivalent, let's see if I can do this, to a stretching and a compression in this direction. So it's a stretching in the along the line between the Earth and the Moon, and a compression in the perpendicular direction. So if this was a jelly-filled donut and you squeezed it and stretched it, it would squirt out jelly on the two ends. Okay, so this is the effect of tides. In the case of the Earth, the tides are weak, so they can influence the oceans that are made of a fluid, but the crust of the Earth is too strong to be affected by tides significantly, so the Earth is not deformed, but the oceans are deformed. Okay. Now the tides of a black hole are extremely strong because we can get a lot closer since it's so compact, and it's also a lot more massive, and the force that it exerts is a lot higher. Nothing can escape the tide of a black hole, not even cartoon characters. So I'll let the movie speak for itself.
Captain's log. Emergency report. We're fast being sucked into the hideous vortex of a black hole.
All the animations are actually scientifically accurate. Everything except the last scene.
But to no avail. Our shipboard computer suggests one last alternative.
So the thing to notice is the stretching of the spacecraft, the stretching of the cartoon characters, and the swirling of all the debris around the black hole before it fell in. The only thing that was not accurate was the compression of the rocket at the end, when it stopped and then it fell in. Okay, so that's what happens to a fluid object like a star that gets too close to a supermassive black hole. That event causes a huge release of energy on a very short time scale of a week or two, and we observe those flares now. We're able to observe them. What I'm going to show you is results from early calculations that try to predict what happened. Okay? So there's the star that gets very close to the black hole. Its trajectory would have taken it around the black hole like this, but the tide gets very strong at position number 2. The star starts to get stretched. By the time it gets here, it loses its integrity because the stretching is too much, and it breaks apart by the time it gets over there. If you run a computer simulation and turn it into a movie, I'll show you how everything happens. That's the star right there, and the red dot represents a black hole. It's going to swing around the star very quickly, and then it breaks up, and it forms a big tail, a stream of debris, which keeps stretching and stretching as the stuff moves away. Some of you may be able to see two colors in the debris. There's a yellow and a white. Half of the debris loses energy, passes it to the other half. So the white stuff lost some energy, the yellow stuff gained some. So the yellow stuff is about half the debris. It can escape to a very large distance, but the loss of energy by the white stuff turns it back and makes it fall back towards the neighborhood of the black hole. And eventually it falls in. So the simulation stops when the first particle falls in. Okay? And for those of you who are astronomers, you recognize this name. It was the first project that he did as a graduate student. Okay. So here's another example of how the tidal force of a black hole influences its stellar neighbor. There's a solar mass black hole here in this cartoon. It could be 10 or 12 times the mass of the sun. It was born next to another star. The two of them are locked into a dance around each other. They revolve around the common center of mass. This star evolved first, it blew up, became a black hole, and then started ripping the outer layers off its companion. You see the tidal deformation, the teardrop shape, and how gas is being pulled out of the outer layers and falling into this black hole. As it falls in, the gas gets extremely hot and emits X-rays, and we can see these binary stars. And eventually, this star will blow up. And if the system survives two explosions, and the two black holes remain bound to each other, they will eventually lose energy by gravitational waves and merge, and we will detect them as sources of gravitational waves. And that's what the next talk is going to be about. So, we make elaborate scenarios that describe the evolution of the two stars, and these are cartoons that describe those scenarios. They show you how the two stars interact with each other, they exchange mass, they go through a brief phase where they're both in a common envelope, then one of them blows up, there's a recoil, then the other star starts to pass mass onto the black hole, then maybe the other star will blow up. The scenario can get a lot more elaborate, and I'm not going to talk about this all that much. But at the very end, you get two black holes revolving around each other, and they are a bright source of gravitational waves. They make waves, they merge, and that's the end of the story for my talk. Thank you.